Hi, in this video, we'll talk about mixed states. So up until now, we had talked about pure states. So pure state is a normalized vector in our Hilbert space. Mixed states are sort of a mixture of pure states. So you can have, for example, so we are talking about mixed states, and one could have an ensemble. Uh, these are probabilities, and these are pure states. So we could have an ensemble of pure states, which leads to a mixture, and it's called a mixed state. So instead of the mixed states being represented as a vector, they are represented by what is known as a density matrix. So they are represented by a density matrix, and it is usually denoted by this symbol rho, and um, it is a positive definite matrix with trace 1. Okay, and how do you generate mixed states? So one way to generate mixed states is just to flip a coin and generate a pure state depending on the outcome of a coin. So one way is to generate them, uh, generate them using pure states. So you pick the pure state with some kind of probability distribution, and that will lead you to get a mixed state. Well, the second way is, suppose you have a bipartite system, then you can measure one of the parts, and suppose the bipartite system is in an entangled state, then the remaining subsystem could be uh, in a mixed state. So by measuring, so one way is generate them using pure state, other is measuring a part of the system. And finally, you could pass a pure state through what is known as a noisy quantum channel, and you could also generate a mixed state. So pass a pure state. So you have a pure state psi, and you have some channel, a quantum channel, and this will sort of lead to a mixed state. So let's move on to some more details of um, the mixed state. Okay, so let's so consider that you have a pure state such as ket 0. Then the you can represent this as a matrix as well. So the density matrix, so let me say that the density matrix corresponding to this state is given by ket 0 bra 0. So the matrix will be 1 0 column vector, and so this will be the projection 1 0 0 0. If you have, on the other hand, if you have a state 1, then the density matrix corresponding to the state 1 is given by the 0 1 column vector and the row vector 0 1. So this will be 0 0 0 1. Now you could have a mixture of the 0 state and a 1 state, let's say a mixture which has with probability half 0 and half 1. Then the density matrix corresponding to this state will be half ket 0 bra 0, that is the density matrix corresponding to the state 0, plus half ket 1 bra 1, right? Now this is actually going to be half 1000 plus 0001. So this is going to be half 1001, which is identity over 2. This is called the maximally mixed state. So this is a mixed state which is called maximally mixed state. Okay. Now let's do the same with the plus and the minus vectors. Suppose you have the plus vector. So let's compute a density matrix rho prime, which is equal mixture of the plus and the minus state. So you get something like this. So you have plus is given by this vector and minus is given by this vector. So you have rho prime is equal to half into, so this will be 1 over 2 outside, and then there will be half 1 1 this column and row vector plus half 1 minus 1 1 minus 1. Okay, so this will be half into half plus half into half minus half minus half. Again, this leads to half 0 0 half, which is equal to identity over 2. So you see that two different ensembles, the ket 0, ket 1 ensemble and the plus minus ensemble, each with probability 1 over 2, leads to the same density matrix. So, well, therefore, one can say that two different ensembles, you can say that Pi get psi I ensemble 1 and the second ensemble Qi phi I could lead to the same density matrix, which means that rho could be summation Pi ket psi I bra psi I, which is also equal to summation Qi ket phi I bra phi I. So this is a possibility, and later we'll come to when these two ensemble lead to the same density matrix. Okay. Um, in general, as I mentioned before, the density matrix, a matrix row, a matrix is a density matrix, which means that it represents a valid state if and only if two conditions are satisfied. One is that rho is a positive definite matrix, and second is that trace rho is equal to 1. So these are the conditions for a state or a density matrix to represent a proper state. Now, what happens when you do a time evolution of a density matrix? So we know what happens when you time evolve a pure state. So if you have, so let's look at this time evolution. So when you have a pure state psi and you evolve it using some unitary u, right, time evolution, this will lead to the state u psi. So there is u is some unitary. And of course, if I take the bra of this, then the time evolution will be the bra psi and the conjugate multiplied by the conjugate of, of u, which is also the inverse. Now, suppose I have a density matrix rho. So suppose I have an initial density matrix rho, which is equal to summation pi get psi I bra psi I. Then the time evolution of this density matrix will be summation over I pi. The ket psi I goes to u psi I, and the bra psi I, so this goes to this, and this bra goes to bra psi I and u dagger. Okay. So I'm just going to rewrite this a little differently. So this is going to be equal to u. I'm going to use the linearity. This is I psi I bra psi I and u dagger. So pi, sorry, which is going to be equal to u rho u dagger. So the time evolution of density matrix um, rho will happen in this fashion. So in general, for pure states, ket psi goes to u ket psi. For a density matrix, rho will go to u rho u dagger. Okay, so what about measurement? So next is measurement. So let's say you have an initial state, which is the ensemble of with probabilities pi and pure state psi. So this is some density matrix, and you measure it using observable A, whose spectral decomposition is given by summation over m times pm. So m are the eigenvectors and pm are the projections onto the eigenspace corresponding to those eigenvectors. So how do I know? So the density matrix rho, initial density matrix, is summation over I ket psi I correct. So now let's see what happens when you measure these states. So let's start with, suppose the initial state was just a pure state. Suppose psi I was the initial state. Then what is the probability of getting outcome m? So let me write that as probability of outcome m, which is P of m. I can write that as P of m. Given, sorry, this is going to be given that the state is I, is we know that from our measurement theory of pure states, this is going to be P psi I PM psi I. okay, which in fact is equal to trace of PM psi I bra psi I. Okay. Now, the probability of getting outcome M, so P of M, will be equal to, by the law of total probability, will be sum over I, P of M given I times Pi. So this is going to be equal to summation Pi I and then trace of PM psi I get psi I. And I can take this probability in because of the linearity of the trace. I can write this as PM summation over I, Pi, which is going to be trace of PM rho. All right, so that is the probability of getting outcome M. So this is the probability of getting outcome M. What about the post-measurement state? So the post-measurement state, uh, so suppose the initial state was psi I. If outcome M was obtained, suppose is initial state, then the outcome, if outcome M is obtained, then this state, as we know, transforms to another state. Let me call that psi I of M, which is going to be equal to, again, by the measurement theory of pure state, this is going to be PM psi over norm of PM psi, which I can write as PM psi over square root of, this should be a square root PM psi. Okay, so now we have to find what will be the post measurement density matrix. So we want to know if if measurement M was obtained, what is this post measurement state or a density matrix? This is going to be equal to summation over I, P I given M. So initial state was I, given measurement obtained was measurement M was obtained, multiplied by, so psi I M get and bra psi I M. Okay, so this will be the post measurement state if outcome M was obtained. Now I can rewrite this so I can rewrite the probability, first probability as probability of M given I into Pi over PM. This is Bayes formula into, and I'm going to substitute uh, this over here. So this is going to be PM psi I, and then this is going to be bra of that. So psi I PM, and then there will be the square root will not be there because it will be multiplied by itself. Right. And then what I'm going to do is substitute this and this from the previous formulas that we have obtained. So if I go here above, I have this PM is trace of PM rho, and PM given I is trace of actually this, right? So this is going to be equal to, so summation over I, pi, which is this, then this is going to be psi I, pm psi I. This is going to be trace rho pm. And then this is going to be pm psi I pm over, this is going to be canceling out. And so this is going to be, I can get this pm sub m outside, summation over I, pi ket psi I bra psi I pm over trace of rho pm. So this is therefore going to be pm rho pm post measurement state, if measurement outcome m was obtained, is going to be that is 1, and probability of getting measurement outcome m, as we saw, was trace of rho pm. So these two are. So we had said earlier that two different ensembles could lead to the same density matrix, as we saw with the ket 0, ket 1 in an equal mixture, and a ket plus and a ket minus in an equal mixture as well. So I could give you another example. For example, this mixture 3 over 4 ket 0. So this is one state. So the 0 state is in the mixture with probability 3 over 4, and the one state is in the mixture with probability 1 over 4. So this ensemble leads to the density matrix 3 over 4 ket 0 bra 0 plus 1 over 4 ket 1 bra 1. But also you could have another mixture, for instance, half square root of 3 over 4 ket 0 plus square root of 1 over 4 ket 1. So this is the state square root of 3 over 4 ket 0 and plus square root of 1 over 4 ket 1 with probability 1 over 2, and the state square root of 3 over 4 ket 0 minus square root of 1 over 4 ket 1. So if you compute the density matrix of this mixture, it will lead to the same density matrix. So what is the connection between these two? So suppose I have a mixture, let's say pi phi I, and another mixture which is qi psi I. When is summation over I pi ket phi I bra phi I is equal to, when is these two density matrix these two mixtures lead to the same density matrix? So the answer is the following. Suppose I take phi I, so let me write phi I tilde equal to summation over, sorry, not summation, but rather square root of pi phi I, and psi I tilde is equal to square root of qi psi I. Then if I can write psi I tilde as some unitary matrix, so sum over j uij, um, sorry, no, this, but rather uij phi summation over j phi j for some unitary matrix U. So suppose this equality holds for some unitary matrix U, U whose entries are given by Uij, then the two ensembles will lead to the same density matrix. So then, uh, then this two ensembles will lead to the same density matrix. Okay, so what we have learned today is about mixed states. So mixed states, as you learned, were a mixture of pure states. And you learned about how they can evolve using the unitary evolution, and what happens when you measure them. Now, next time, what we look at is the reduced density matrix, and how to compute the reduced density matrix. Now, if I have a product state, then it's easy to say what each subsystem states are. But if I have a entangled state, then it's not so clear what are the individual states, and that's where the reduced density matrix will come in play, and we learn an operation called the partial trace operation, which will help us understand the reduced density matrix.